The first type of transfer function, or so-called building block, that we will consider is when the transfer function is either a positive or a negative constant, or so-called gain. So let's call the, when the transfer function has a positive gain, let's call that T1 of S is equal to K, and T, when it's a negative gain, we call it a T2 of S is equal to negative K. Okay, I know I've explained this in class, but I want to go over it again for the sake of those who pressed the snooze button one too many times. Okay, so let's consider the first transfer function when it's a positive constant. Of course, the first step is to set S equal to j omega to get the frequency response transfer function. So let's do that. And that, of course, is just then again k, because this transfer function is not a function of frequency. And then the second step is to take the magnitude of the transfer function. Then if we do that, well, the magnitude is just the real part squared plus the imaginary part squared, and that is of course just equal to k. We can also get the phase angle if we do that. Well, the phase angle is just the arctangent of the real part, or the imaginary part, which is 0 over the real part, which is k, and that is just the arctangent of 0 is equal to 0. We can also get this magnitude and phase when we plot the frequency response transfer function in the imaginary plane or complex plane. I think it's a good way to illustrate this. So that's the imaginary part. So we know we've got this T j omega is equal to k. So we know if you've got a positive constant, a real constant, so it will lie somewhere on this, a real line. Okay. So we know that the distance from the origin to this point is the magnitude, and that's of course just k. And the angle between this line and the real line is the phase, and that is of course just 0 degrees. Okay. Before we start drawing this, let's quickly consider the transfer function where we have a negative gain. So again, we do the first step. We set S equal to j omega, and that's of course just equal to negative k again. If we take the magnitude, well, that's again the real part squared plus the imaginary part squared, and that turns out to be k again. And if we take the phase angle, again that's the arctangent of the imaginary part, which is 0 over the real part, which is negative k. And your first guess would be that this is again 0 degrees, but in fact it's not, and we can prove that it's not by again plotting the same or plotting the frequency response transfer function, which is a complex number in the complex plane. So we know that Tj omega is equal to negative k. So it's this time the value lies on the negative real line. Again, the magnitude is the distance from the origin, so this magnitude is just k. And we know that the phase angle is the angle between this line and the real line. So we know that that is negative 180 degrees. You can also use 180 degrees, but it's a convention to use negative 180. Okay, so this is in fact negative 180 degrees. Okay, we can now start drawing the magnitude and phase plots. Just try to do this neatly. Well, let's try and okay, so we have to recall that on the magnitude axis we plot it in decibel scale, so it should be 20 log of the magnitude of the frequency response transfer function, and this is just omega plotted on a log scale. Okay, let's have a look at what our magnitude was for positive k. Well, that's just, if we take, we know that the magnitude is equal of the frequency response transfer function is k, so we have to take 20 log of that, and that's just equal to 20 log of k. Okay, so we can plot it somewhere. So that's our magnitude. So that value is equal to 20 log of k. If we look at the magnitude of the frequency, if the transfer function is a negative gain, we also saw that the magnitude is equal to k. So our magnitude, when we have a negative gain, is also 20 log k. Okay, if you draw the phase plot, well, the phase is usually, the phase axis is usually plotted in degrees, and it's a linear scale. This is again omega. Okay, if we look at when our transfer function is a positive k, we see that the angle is just 0 degrees. That is in fact decibels. Okay, so our phase plot for when it's a positive k just looks like that. And if we look at what the angle is when it's a negative k, we see it's a negative 180 degrees. Okay, and that completes the magnitude and phase plots of the first type of transfer function that we consider. Okay. When we do an example, we can clearly show that it's quite easy to plot this. Let's just do an example. Let's use T of S is equal to, well, let's just use a value of 15 or something. Okay, so first step is to take S equal to j omega that's of course equal to 15 again. And the magnitude will also be 15. Okay, to plot it on the decibel scale, we have to take 20 log of that. So this is on 20 log J omega. Okay, so we have to work out what 20 log of 15 is. And if you go work that out, that should be around 23.5 decibels. Okay, so we can plot it somewhere here. So that should be around 23.5 decibels. And that is for both when this transfer function A is equal to 15 and when that is equal to negative 15. The phase is of course a little bit different depending on whether it's a positive or a negative. And we don't have to really work out anything in this case, because we know for a positive constant, we know that the phase will be 0, as we proved above. And for a negative constant, the phase will be negative 180 degrees. Okay,